1, 2, 3. Dear colleagues, kindly remind you that today we will not have evening informal quiz, but traditionally test we will have.
Seminar will be also a continuation of Alexander Skrotin's lecture, but this time on page matching. So in this seminar, we will implement page matching in both conditional and conditional settings. Learn learn the differences between conditional and conditional page matchings, and learn some other properties of page matching methods, for example, like related to its volatility coefficient. So we will go through two examples. First example is two example. It will be a Gaussian mixture to a Gaussian mixture. So it's like a general translation from one distribution to another distribution. We will learn unconditional page matching, compare them, and vary the volatility coefficients for page matching methods. And then we will try both page matching methods on the image inverse problem, which will be in painting on flowers 102 dataset. And again, we will learn conditional page matchings, compare them, and see that they actually differ. See the difference between them. So first of all, I would like to recap some theory. So like the lecture of Alexander was not that far ago, so I will be like a bit faster. But first, let's recap the diffusion bridges and mixture diffusion bridges. So remember that we have some kind of pair diffusion process Q that is formulated as this diffusion with its drift function and volatility coefficient, and it has some related distribution Q, which is the distribution of diffusion process at some particular time points. And the important instance of this distribution Q of stochastic process is this Q x big T conditioned on x small t. This would be used for a Dubas transform, and it's basically the distribution of random variable x big T at time t conditioned on x small t at time t. So then, if we have this pair process, we can make it to start and end at some particular points, Alexander said, by employing Dubas transform. So I recap that Dubas transform would look like this. So the only thing that differs from the prior process is this definition of this gradient of logarithm of distribution Q, basically this score function of stochastic process, if you would. Yeah, so basically this helps us to see into the future of the process and the condition on this future. And of course, we start from x0. And we call such thing a diffusion bridge. Then, well, diffusion bridges are great, but they do start and end at one particular point. So to incorporate this diffusion bridges into the framework when we have one distribution at the start and another distribution at the end, and not the delta function, so like just some points, we do make a mixture of diffusion bridges, which would be just the conditioned diffusion bridge, conditioned on points x0 and x1, or x big T, and weighted by our initial distribution P on x0 and xt. So as Alexander said, this distribution P on x0 and xt is actually pretty important because it defines our mixture diffusion bridges, and it gives us some kind of a provision was used in page matching in our seminar, where we have been exploring this particular distribution in independence setting, mini-batch setting, mini-batch optimal transport setting, and mini-batch anti-optimal transport setting. So this is basically exactly the same distribution as it was in flow matching, but now we use it in bridge matching setting. And so yeah, we get this acyclical process, which is a stochastic process that starts at distribution P0 and ends on distribution Pt. So okay, it has these two distributions, but there is a problem. We cannot sample from this stochastic process because it is not a regular Markovian diffusion. Like we just do not have a way to sample from it, to sample like xt given x0 based on it. So what do we want here is take this wonderful acyclical process and learn a approximate way to and learn a stochastic differential equation that is very similar to this acyclical process and that we can actually sample from. Yeah, this can be done by projection. They will later. And so where we would, for simplicity, use Brownian motion as a prior process, which would be defined just by, yeah, we just add noise to our data. And this would be just a Brownian motion with some volatility epsilon that will control the amount of stochasticity in our prior model. And the final time would be equal to 1 because it's simpler. And so this score function, which with this scary gradient of logarithm of distribution, would be of this relatively simple form. Yeah, so you see, just x1 minus xt 1 minus t. Yeah, and as Alexander said, in the case where we take this Brownian motion and limiting to 0, that volatility converges to 0, then this particular quantity would be reduced to flow matchings x1 minus x0. So yeah, you can also see a flow matching as a particular case of this bridge matching framework. So okay, great. Now we have all this prior process, diffusion bridge, Dubas transform, and reciprocal processes. Then we want to learn a stochastic differential equation that tries to somehow mimic the behavior of this mixture of bridges that we just derived. Okay, cool. How do we do it? So we can do this Markovian projection, again, which Alexander told about. So basically, this Markovian projection tries to learn a stochastic differential equation with this alternated drift. So again, this is different from the prior process just by this expectation of gradient of logarithm function, gradient with expectation of this score function. This is the only difference. And if we have this expectation of gradient of logarithm of stochastic distribution, then we can sample from it explicitly by just inferring like numerical solvers for stochastic differential equations. So okay, great. The question, as Alexander said, this distribution x big T, this q on x big T dependent on x small t, is unavailable to sample from. And hence you cannot just estimate this quantity by employing Monte Carlo estimation. But what you can do, you can actually learn it by solving an optimization problem, which will be just as in flow matching case, just a L2 like L2 regression or like just minimizing of mean squared error loss, which is also like very easy. Yeah, so we overall final optimization problem that we would solve, we'll have this view, which is the expectation over xt and x0, where they are sampled from distribution of p on x0 and xt, and you sample t from uniform distribution on time between 0 and 1, just like in flow matching case, and you solve a regression problem, just as in flow matching case, but the regression target is a bit different than in flow matching case. So in flow matching case, it is x1 minus x0, and in this case, it will be x1 minus xt divided by 1 minus t. Yeah, so it would look like this in our particular seminar setup. And one of the things that I should mention is that, again, just as in flow matching's case, despite this problem being a regression problem, the minimum of this loss is not 0. It is greater than 0. And compared to the flow matching case, where we could find a case where the optimal value of this loss would be 0, it is not possible in bridge matching's case. In bridge matching case, it would be always greater than 0. Well, okay. So to kind of sum it up, we have distributions P0 and Pt. We have some kind of prior process Q, which is defined as, again, this diffusion. Then we have our diffusion bridge, which is the prior diffusion process, but conditioned on start and end on some points, x0 and x1. Yeah, so we construct a mixture of this conditional diffusion processes and yeah, learn a stochastic differential equation that mimics the reciprocal process behavior, and again, just as in flow matching case, it would not entirely mimic reciprocal process behavior, but it would go through the same marginals as the reciprocal process. For our particular case, this is interesting because we can provably start at distribution P0 and end at distribution Pt. So we always know that we start at some particular distribution and end at some particular distribution, and these distributions will have the same marginals as data we put into our algorithm. So this would give us a legitimate generator of samples. And since what we basically learn is a stochastic differential equation, as the ordinary differential equation, we can parameterize it by just the drift function. So again, let me go over here. Yeah, so we have to just parameterize this fxt plus this math expectation and learn it via this xt. And here is a square missing. And the beautiful thing about bridge matching is that we don't have to learn the volatility coefficient because it stays the same as in the prior process in this one. So since in our case we have a Brownian motion process, then the volatility coefficient will be the square root of epsilon. And in our resulting SDE, it will be also a square root of epsilon. And so yeah, we just parameterize our vector field by neural network, solve a regression problem, and everything is great, everything is awesome. We have a stochastic differential equation that goes from one distribution to another distribution. So okay, this is unconditional bridge matching. There is another version of bridge matching called conditional bridge matching, which differs from the unconditional bridge matching by just a little bit. What we do is just we alternate the vector field a bit and add conditioning on x0, aka starting point, to our vector field. So like in practice, everything else stays just the same. We just alter the neural network that we use as the vector field parameterization for vector field parameterization. But despite such little practical changes, actually the theoretical qualities of learning process differs very much, because I want you to recap that unconditional batch matching, like regular batch matching, do not preserve data distribution. So again, as Alexander told you, it does not preserve the data distribution. However, conditional batch matching actually does preserve the data distribution, because you just learn a family of diffusion models that start at some x0 and go to some conditional distribution xt given x0. And this is a very useful in practice fact, and this is the main difference between unconditional for matching and conditional for matching. Like the fact that one preserves the data distribution and the other does not preserve the conditional data distribution. You can use this fact as much as you want. This can be both good and bad depending on your problem. And yeah, so next we will implement this both batch matchings, both conditional and conditional, and take a look at their performance in practice. First, let's start the implementation of our batch matching. And the first thing that we want to do is to implement sampling of points for from the Brownian bridge to train from. So I want you to recap that for the optimization of this regression batch matching clause, one has to sample x1, x0, t, and actually xt also. So you have to also sample xt stochastically from a Brownian bridge, which in our case will look like this. So this is again very similar to flow matching, except for one thing, that in flow matching this interpolation is deterministic and not stochastic as in the Brownian bridge case. So if we do set the volatility coefficient epsilon to 0, then we very easily get the flow matching interpolation. And yeah, like this analogy goes for many things with batch matching, that flow matching is just the particular case of batch matching with volatility coefficient going to 0. And so the implementation of sampling from Brownian bridge is very similar to the flow matching one, because we do this have these coefficients, which is 1 minus t and t, just as in flow matching, but we add also a stochastic coefficient, which would be t multiplied by 1 minus t multiplied by volatility coefficient epsilon, and we sample some random noise. And the resulting xt will look like this. So if we will do like this and delete the stochastic part, it would be essentially a flow matching interpolation that we have written this morning. But yeah, for the stochastic differential equation in batch matching, we would have to add a stochasticity to our interpolation. So, okay. Cool. Now, and for the ordinary differential equations, just as in flow matching case, there are many very good ordinary differential equation solvers, etc. However, for the stochastic differential equations, it is not that easy. There do not exist like a lot of successful higher order methods for sampling from a stochastic differential equation. So we would have to go with just usual Euler sampler. So yeah, we just have to go with regular Euler sampler. And another cool trick that we will use here is the posterior sampling. So instead of learning the vector field, just as like I've showed you over here, which should be x1 minus xt divided by 1 minus t, it would be more computationally efficient to learn x1. And we can actually do it because we already given xt, 1 minus, and y minus t. So we can put it out of the equation and learn just the x1, which should be also very nice for our neural network because, well, this diff function x1 minus xt divided by y minus t can be, can have various magnitudes and can be of many forms. And x1, which is the data, is just the data. So it is very nice for a neural network to all steps tries to learn the same exact thing, but with a little bit of alternation. And yeah, a little bit of a question to an audience. So can you maybe see in this particular loss function, this particular optimization problem, a computational problem? Yeah, so what can go computationally wrong in that objective? I will like cancel it a bit. Yeah.
When t equals 1, the right is divided by 0.
Yeah. And if t goes to 1, then yeah, so we cannot we will not have like t equal 1 here because it's actually like undefined with this t. But yeah, so computationally, if you go near this t near 1, we will have computational problems. And like in practice, we go from 0 to t like equal to 0.999999, and hope that it goes all right. But still, this can be like a computationally tricky problem. And so switching to the prediction of x1 would be a very nice thing because, as I would show earlier, yeah, so then loss would look like this. So it just learns the x1. And then we just add this division and xt later, or actually do not add it. So yeah, great. In terms of sampling, on each sampling step, we would go with the something very similar to the earlier sampler, but we will start it from point xt. Then we will predict x1 based on xt. We predict, so we can predict the endpoint and go somewhere in the middle by a closed form posterior sampling. So that way we can predict the resulting data and still sample points somewhere in the middle. And yeah, so this would be this trick is used in many diffusion models to enhance their performance, also known as preconditioning, I guess. So yeah, in practice, how this sampling goes, we go for the so we input the number of integration steps that we want, which is also known as NFE, or number of function evaluations. So basically, on each integration step, we would need to do one function evaluation. That's why it's called number of function evaluations, so NFE. Then we have our time grid, which will be from 0 to 1 divided by 100. Do a little bit of steps of this, like delta t, which would be 1 divided by 100. Infer our neural network. Predict some STD mean and do a posterior sampling. Again, posterior sampling is actually closed form, so the formula is a little bit different from the Brownian motion, but not for much. So basically, you can given xt, you can just sample from normal distribution a point somewhere in the middle. And you just do it like 100 times, and at the end you have your SD trajectory. So basically, this is equivalent to Euler sampler, but just like alternated a bit. Okay, so yeah, as far as I've said, if you predict the data instead of learning particular the vector field, then your loss function will alter a bit because, and it would look like this, because now you learn the x1 data and not the vector field. And you would not have any unexpected computational problems with like this t close to 1 during training. So, and again, yeah, minimum with this loss is not 0, which is like important, just as for the upper loss. So at the end, the implementation of loss function will be just as follows. We like have xt hat, which is the prediction of vector, the prediction of x1 by our vector field model, and it will be regressed onto x1. So like again, very simple regression problem, very simple to implement. And so yeah, we've gone through all the needed functions for finally building the bridge matching. And now we can build the class of bridge matching and combine it all into one thing. So our bridge matching class, it would consist of a neural network, of course, which will be some kind of a UNet. The epsilon, which is the volatility coefficient, and the fact that it is either conditioned or not. So I recap that if your bridge matching is conditioned, then the vector field neural network, or like x1 predictor neural network, also has an x0, aka start of your diffusion trajectory point, as an input. So you would need to have a different neural network architecture for this. So okay, then we just as for flow matching, we need to sample points xt to calculate our loss on it, and we do this by Brownian bridge. And then we have our train step, which inputs data, has data as an input x0 and x1 and t, which are sampled from data distributions and from time distribution. And then we calculate loss, and yeah, that's it. And we have sampling from posterior function as well. So yeah, we finally did it. We finally implemented the bridge matching. Now we will try it on a toy two-dimensional example. So I don't know, some questions about the implementation of bridge matching so far. Okay, then I will go to the experiments. Okay, so now we will test our bridge matching and conditional bridge matching on toy two-dimensional problem, which would be two Gaussians to two Gaussians. Yeah, so we start from the blue distribution and try to end at the red distribution. So these two distributions are very, very similar, but what is different compared to the, for example, previous two experiment with flow matching is the fact that both of the distributions that we have, both starting and ending distributions, are multimodal. And so it would lead. So let's draw a Brownian bridge between some samples from these points, and you will see how do the Brownian bridge trajectories look at these particular distributions, and yeah, you will see that they intersect quite heavily. Yeah, so this is the Brownian bridge trajectories for different points from these two distributions with different volatility coefficients. So let's take a look at the first one. So what you can see is remarkable here that that trajectories do intersect. So they have some kind of this crest in the middle, and trajectory intersection is like a cornerstone of bridge matching and flow matching methods, because some of the methods do preserve this intersection, some methods do not preserve this intersection. And yeah, you can see at the volatility of 0.1, the trajectories are not that stochastic. They are like almost straight, let's say. They have some kind of this like stochasticity part, but mostly they are straight. And so if we take a volatility coefficient of 1, which is 10 times bigger, you can see that actually volatility starts to grow up, and our diffusion trajectories, Brownian bridge trajectories, start being more and more stochastic. So yeah, all of these things are because of all of this, say, sharp edges are because of stochasticity. But trajectories do still intersect. And for the epsilon of volatility coefficient of 10, which is like a lot, you can see that yeah, trajectories are very, very stochastic. It is like almost impossible to actually understand what trajectory is which trajectory is which trajectory, because they do intersect very heavily. And yeah, so very, very noisy trajectories. And yeah, I recap that we can actually learn flow matching with bridge matching with different volatility coefficients. So basically, we can learn a flow matching with each of these volatility coefficients, and it would be like different bridge matchings with different properties. So let's pick the middle volatility coefficient of 1 and try to learn bridge matching on this type problem with it. Yeah. Okay, it takes a lot of time. So I will just show you the result, that if we will learn a flow matching or bridge matching on the volatility coefficient of 1, then you can see that it fits the resulting distribution very well. So the yellow points are the generated points from our bridge matching model, and they should be lying approximately in the same area as red points, and you see that they actually do. So this means that we have optimized our bridge matching quite well. But fitting the final distribution is one thing. Now let's take a look at the trajectories, which will be quite interesting. So yeah, so we have these interesting trajectories that do have this some kind of center. So as to recap on what data we have learned our bridge matching, we have learned our bridge matching. As you can see, there are intersection trajectories, and that means that our learned bridge matching also has some kind of a prior to making similar intersections. However, as Alexander told, the unconditional bridge matching that we have just learned does not preserve the initial data distribution. It alternates it, and it alternates it in the favor of less intersection of trajectories and shorter generation paths. So, for example, this like long path is a lot longer than this shorter path. So the unconditional bridge matching will go through this path if it is possible. Yeah, it has less probability of intersection. with our generation trajectories. So we for flow matching, actually the intersections between generation trajectories are non-existent because it is ordinary differential equation, and the trajectories of ordinary differential equations do not intersect. But for the stochastic differential equation, it is possible, so that the generation trajectories will intersect. So we're here, somewhere here, flow matching, but for bridge matching, it is okay. So yeah, and this is the unconditional bridge matching. So to kind of conclude the experiment, so we have learned the bridge matching, which has successfully learned the translation from two Gaussian distribution to another two Gaussian distribution, and which changed the data plan in favor of non-intersection trajectories. So, okay. But the different thing will happen with conditional bridge matching. So let's take a look at conditional bridge matching. So again, we can use almost the same thing, but we would need a different neural network architecture. We should be like a little bit alternated MLP in our case. So yeah, we can launch the learning. Yeah, it will take a lot of time, but yeah, I can show you the results nevertheless. So this is again the picture of how well the conditional bridge matching fits the target distribution, and you can see that it fits the target distribution as well as the unconditional bridge matching. But there is a difference, and the difference lies not in the fitting with final distributions marginals, because both conditional and unconditional bridge matching do that pretty well. The difference between conditional and conditional bridge matching lies in the trajectories. So yeah, you can take a look at these trajectories and see that they are very different from the regular bridge matching plans. Why? Because they intersect, and they intersect a lot. So this thing in the middle is the same as for the initial data distribution. And like indeed, actually, this particular like generation trajectories do very much look alike as the data that we have trained our bridge matching on. So I will recap that it looks like this. And yeah, this is like very, very similar to the conditional bridge matching that we have just learned. And another beautiful thing that you can see here is that actually the trajectories are relatively straight. Just as the interpolation that we have used to train our bridge matching on. But they do intersect pretty heavily. So as you can see, the distribution of data that we have used to train our bridge matching on pretty much is being conserved by the conditional bridge matching, and this can be both good thing and the bad thing. So yeah, and let us made a mistake. So let's make a conclusion out of this experiment. So both bridge matching methods, both conditional and unconditional, do learn final distribution pretty well. So they both learn the red distribution of two Gaussians. This is great. In that sense, they are pretty much the same. But conditional and unconditional bridge matchings are different in terms of preserving the initial data plan P. So regular batch matching, aka unconditional batch matching, has shorter and let's say non-intersecting trajectories, because let's say that they have less probability of intersecting than for the conditional batch matching. And so they do preserve the data plan P, and since they do not preserve the plan P, and since conditional batch matching does not preserve the plan P, then it can be used for the unpaired learning, because it can alternate this plan P and try to find the optimal, in a sense, instead of showing bridges, actually, one. And conditional batch matching has longer and trajectories that with higher probability of intersection, and this generation plan is the same as the data. Yeah, so the plus is that we conserve the data plan, which can be a good thing depending on your task. But the bad thing also can be that it preserves the initial data plan, because it depends basically on the task that you have. So if you want your model to preserve the data plan, that is good. If you do not want it to preserve it, then it is bad. And one particular case when preserving of initial plan is bad is unpaired learning, because conditional batch matching will not have a possibility to kind of learn a new relatively optimal plan, because it does not alternate it. You just set the data plan and that's it. You do not change it after. So again, I want to make some kind of emphasis on this, so that conditional batch matching does preserve the initial transport plan and have intersecting trajectories, while the unconditional batch matching does not preserve the transport plan. As you can see, points from this upper blue Gaussian do not go to the lower red Gaussian as they did in the data. This unconditional batch matching has shorter trajectories, which also can be a good thing. Okay. Next we will take a look at the image-based task. So maybe some questions before the second part of the seminar. Okay. Then I will go to the image-based problem, which is indeed like a problem that you in reality can solve using batch matching. So it is not a toy problem in some sense. So we will take a look at the problem of painting on Flowers 102 dataset in 64 by 64 resolution. So what is painting? It is when you have some kind of an image, or I can show. If you have some kind of an image, and but this image does not have a center. So the center of this image is just black. But you want to generate you want to fill this blank space with something that suits the surrounding image. So, for example, for this purple flower, it is logical that instead of this black square, there should be a part of the flower of a purple color. And yeah, this is like a relatively hard image inverse problem. That is more suited for the conditional batch matching, actually. So yeah, let's learn both unconditional and conditional batch matching models on this painting task problem, and take a look at their difference. So So let's first prepare the data. Let's prepare the data, which would be a flowers 102 dataset, which is the relatively known dataset, consists of 102 classes of flowers. We will reshape it into 64 by 64 shape and try to delete the center of such an image to make a pair of image of corrupted image with blank space in the center, and the ground truth clean image with filled center. So yep. Let's take a look at the result. So yeah, again, as you can see, on the top is the clean image, and at the bottom is corrupted image. And this would be the data pairing for our bridge matching that we would use further. So in a sense, remember these two Gaussians, one blue, another is red. And so for our case, the upper row is red distribution, so the target distribution that we want to go to, and the bottom row is the star distribution that we start from, aka this blue Gaussian distribution. Okay. Then, as for the toy case, let's take a look at some Brownian bridge trajectories. So again, Brownian bridge is just the stochastic interpolation between x0 and x1, between some data and some data. And here you can see the interpolation, stochastic interpolation between corrupted image without center and with clean image. So yeah, as you can see, this since it is a linear interpolation, the blank square disappears quite well, not as fast. It is like a little bit present up until the end. And also you can see that these images are noisy. This is because we add a noise to our linear interpolation. So one can say that, well, these images are noisy. The noisy images are bad. Why don't we use deterministic interpolation? So these images would be clean. I would say that the additional stochasticity actually adds as sometimes additional stochasticity is good for your model. It gives you more training data. And for example, for this image inverse problems, you may have not enough data to train your model on, and this stochasticity also gives you additional data to train on. And also the stochasticity will help during the generation. So without stochasticity, it would be again just flow matching, and flow matching is actually a relatively bad model to perform data-to-data translation because of lack of stochasticity actually. And so yeah, you can see the Brownian bridge interpolation with higher stochastic coefficient. You can see that it becomes more and more noisier. And yeah, so the blank square in the middle disappears somewhere in the middle of trajectory because it's just replaced by the noise. And for even higher volatility coefficient, I think you cannot even see the difference between one part of the trajectory and the others because they have predominant noise. So noise is the predominant force here, and yeah, it's hard to distinguish one sample from another because of the noise. So in practice, what volatility coefficient would you use? So so first of all, you can guess that such a high volatility coefficient, such as this, is quite bad because the stochasticity is too high, and it would be hard to learn a model on such stochastic data. So this stochasticity, middle stochasticity, looks pretty much normal. And yeah, actually you can, I think, learn a like relatively good batch matching with this stochasticity for this problem. But practice shows that the lower volatility coefficient, the better, in particular for the inverse problems. And for example, one could use like even lower volatility coefficients, for example, like 10 to the power minus 3, and it will still be okay. Like performance would actually be even better than now. But we would use the volatility coefficient of 0.1 and learn our batch matching models with it. So again, we just implement model, and we take a unit as a neural network. So as I said previously, I've taken this unit to the model from the diffusers library, which is relatively kind of a diffusion-based or flow matching-based generative modeling. And yeah, what we would do here is just learn our batch matching. So let me like comment all this. Yeah, very slow. Okay, seems like I will not have a possibility to run a single cell in this seminar, but okay, I will just show you the results. So yeah, we just set up a usual train data loader that outputs the clean data, and then we just using this corrupt function just cut out the middle of this clean data and make this data pairing. So again, we would want to make a diffusion bridge from the probability distribution of images with cutout middle to the distribution of images with not cutout middle, like normal, clean images. And yeah, again, we do all the regular things. We do sample data, we do sample time t, and do a batch matching train step, which I have defined like in the beginning of the seminar. Yep. Okay. Yeah, like learning of this model like actually takes relatively a lot of time because the neural network is relatively heavy. For this problem, it is like, yeah, this is not entirely a toy problem, so such time is actually like pretty low. You can learn like neural network for several hours for this particular problem and still see some improvements. But yeah, so this is a small neural network learned for 7 minutes on 20 epochs. And here's the result. So let me maybe you can take a look and maybe some of you can say what. So the first one is the clean image. The second one is the corrupted image with cutout middle. And the third one is generation. So what can you say about generated data? Can one like notice what is the problem with generated data? Okay. So it is very blurry. It is very blurry.
Sorry, Sergey, do you hear me? I'm here.
Okay.
So yeah, it was my question. We conceive that our not only square in the center, but all background is just blurred in our generations. Did you hear me?
No, like it's hard for me to hear.
Okay, I will speak a bit louder. We can see that whole background just blurry stuff and so on. So it's just because our model is small and not capable to handle it out, or by something else.
Yeah, well, it will certainly be better if the model will be more parameterized, if the model will be more expressive. Yeah, so for example, for the unconditional batch matching, for conditional batch matching, we would use exactly the same neural network with like almost approximately the same number of parameters, and the result will look quite sharp. Okay. So this is also can be considered as some kind of batch matching property, and yeah. So the problem here is that batch matching starts from this point x0, and it forgets it like pretty quickly, and that leads to some kind of blurry trajectories, blurry generations. And so, but actually, you can see that it infills the center with pretty good quality. So, for example, here in this white flower, there should be a purple middle, and it generates something that looks like purple middle. So in this particular example, on the center should be a part of purple flower, and yeah, there actually is a part of the purple flower. So in that sense, batch matching works pretty well. It feels pretty well, but the image is blurry. So okay, let's see, will conditional batch matching help us? So again, we all do almost the same thing, but as I've already said, the neural network architecture for the conditional batch matching will be a bit different. It will have xt and x0 as an input. So the dimensionality of data as an input is 2 times bigger. So we would have to a bit of change the number of in channels for our neural network. So basically what we do is concatenate our 2 images. So the one image has the channel of 3, the other image has the channel of 3. Also, we just concatenate there by their channel dimension and get just 6 channels instead of 3. The other part of the neural network stays exactly the same. Yeah, and then we just learn it as a regular batch matching. Let's take a look at results. Yeah, so this is like particular the same flowers as for the previous batch matching, but as you can see, the images are much less blurry. And yeah, so as you can see, for example, the purple middle in this flower is being reconstructed with better quality. So yeah, the main thing here is that flowers do not look blurry anymore, and hence this just more visually attractive and can be considered as a relatively good solution to the problem. So this happens because conditional batch matching is better for general image-to-image translation problems. So general image-to-image translation problems do include problems like image painting, for example, day-to-night translation, for example, like horse to zebra translations, like or for example, coloring of shoes. And because the data that you have in these problems actually has relatively good prior data distribution that you get from your data set, because you will likely change it in the wrong way. And in that particular case, the conditional matching is better because it. yeah, so the result is good and not blurry, and let's make some kind of a conclusion for the in-painting experiment. So regular batch matching does not produce good samples because the images are blurry. And in that sense, batch matching is ill-suited for general image-to-image translation problems, for example, like in painting, and general domain translation, for example, like day-to-night image translation and image coloring, because it changes the paired data coupling in favor of shorter trajectories. But that regular batch matching is good at. The example of such problems is, for example, image super resolution and, for example, image denoising. Because in these particular problems, the shorter trajectories are actually a good thing, because the result of generation should be close to the initial data that you have as an input. So, like in in denoising, the expectation of your clean data should be very similar to the noised version that you receive. And for such inverse problems, like image super resolution and image noising, the batch matching is better. And conditional batch matching, it produces better samples and almost solves the problem of in-painting, and is generally more suitable for general image-to-image translation problems, like day-to-night translation, horses-to-Zimbo translation, coloring, and etc. And performs a bit worse than regular and conditional batch matching on problems such as image denoising and image super resolution. But yeah, so and one note, like one of the reasons why actually conditional batch matching here performs better than unconditional is because it learns the delta between input data and the resulting data. Because it also has x0 as a part of an input, it can remember the start of your trajectory, and hence it has to learn the more of the delta to the real data, other than just real data distribution. And this is like in computational sense is more suitable for neural networks to do. And so overall conclusions for the seminar. Batch matching it doesn't conserve the paired data coupling, learn shorter trajectories, and good for problems with such as image super resolution and image denoising, and applicable for unpaired learning. So again, the first part, the fact that it does not preserve the paired data coupling, it can be both good and bad. Like good in the sense that it learns shorter trajectories, bad in the sense that if you have good data coupling, then it can be altered by the batch matching. And the conditional batch matching, it conserves the paired data coupling, which again can be both good and bad. It learns longer trajectories, or better to say, it does not alternate the generation plan in the favor of shorter trajectories as regular batch matching does. This conditional batch matching is good for general image-to-image translation problems, such as image in painting, day-to-night translation, horses-to-zebra translation, and etc. And conditional batch matching data plan, and hence cannot optimize over the data plan, which we need for the unpaired learning. And yeah, so I guess that's it. That's it for the seminar. Here are some related materials, which I think like also Alexander have shared. So yeah, I think that's it. Thank you.
Hey guys, it's the question time. Do you have any questions? Question? The microphone, people, please use it.
Okay, thank you for your seminar. I have a question regarding the volatility coefficient. So you said like the lower it is, the better is generation usually. But when there is no coefficient, then generation is bad. So there exists some local minima, right?
Yeah, so in general there exists some kind of local minima, but I would say it is different for every problem. So for example, for some kind of a toy problem, you would not see like very much of a difference between different volatility coefficients. So when it is like reasonable, so it's like not as noisy as this one. Okay, in general, there exists some kind of like this optimal volatility coefficient that is good for your problem. So, for example, for image-to-image translation problems, it is relatively low. It is like 10 to the power of -3 or -4, I think. So, like, you can see that if you will plot a trajectory, it will be like with almost no noise. And like in that sense, it seems like, oh, if we delete the noise, nothing will happen, everything will be just the same. But actually, no, this like little noise actually helps pretty much and helps to, and if you take noise which is like lower, even like lower, not exactly zero, but lower, it would have worse performance. So yeah, like to sum it up, there exists some kind of optimal coefficient, but it is like different for many problems, and maybe there are like not one optimal coefficient, but yeah.
Yeah, thank you for the seminar. And I have a question about to transform this model to three-dimensional case. As understood, we only need to change UNet architecture. And after that, it also should work. Do you feel some nuances in transferring to three-dimensional case, for example, for tomography?
Yeah, well, the only thing they would have to do is, I think, just like put 3 instead of 2 here.
This is the only change, yeah.
Yeah, like in theory, yes. In practice, well, I don't know. In practice, I don't know. Well, it depends on the specific of problem that you use. Like if you use it for some kind of inverse problem or like domain translation on the 3D data, like tomography. So yeah, I think it depends on your particular problem. So maybe you would have to add some kind of like tricks to make your performance better. But in general, you just have to. Like,
for example, for super resolution.
Oh, for super resolution, well, I have not tried a super resolution on 3-dimensional data, but I think yeah, just changing the neural network and playing with a bit with this volatility coefficient would be like maybe enough to set some kind of a baseline. So yeah, and then you can go further in some kind of like maybe empirical things and to make your like bridge matching model work better for your particular case, I would say.
Okay, yeah, thank you.
Have 1, 2, 3. Do we have our questions? Let's check questions from online. Do we have questions from online? Okay, so I suppose we can finish our today practice. Thank you very much, Sergey. So we start our next lecture according to our schedule at 3:30.